Welcome back to another fundamental video. Last time we were looking at how to write an equation, calculate the gradient of the y-intercept of our line. We looked at two methods. One was a successful method and one I sucked at. So here what we need to do is just fill in the way that we calculated the best and the worst fit. You should do all of your working on the graph and then just copy it over into this sheet here if you're using these sheets. One thing I didn't talk about was the units. So the units here that I've written is seconds per square root of meter, and the way I work that out is by using the equation for calculating the gradient, which is rise over run, and then just writing the units that are on the rising axis, which is the time period axis. The units are seconds here in brackets. So I've put that on the top and I've divided it by the units that are on the running axis, which is square root of m down here on the square root of L axis. Okay, so we end up with seconds over square root of m. I've also copied in my two y-intercepts of the best fit and of the worst fit. And the units for those, because they are the y-intercepts, it's just the units of the y or the vertical axis. Again, on the vertical axis, the units are seconds. So that's these two values here. Then I've gone through and showed the way that I've calculated the uncertainties in the gradient and the uncertainties in the y-intercept. The next step is to write the equation for the line. So the way we do this is similar to for 2.1, physics 2.1. We start with the generic equation for a line. Y, which is the value on the vertical axis, equals m, which is the gradient, x, which is the value on the horizontal axis, plus c, which is the y-intercept. So again, I can look at my graph for this. On the vertical axis of my graph, I've got time period, so I'm putting that in place of y, so capital T, equals m is my gradient. My gradient is written up here, so it's the gradient of my best fit line. We do this slightly different this year. We need to put this in brackets because we have a value for the gradient, but we now also have an uncertainty in the gradient down here. So my uncertainty is plus or minus 0.1. The reason I scribbled out this other 0 here is because this is to one significant figure of accuracy, and my gradient should be rounded to the same number of decimal places as my uncertainty. You'll notice that I haven't put in any units into the equation. We don't need the units. Cool, so the stuff in the brackets represents the gradient m. Then x, again we just put the value that's on the x horizontal axis, which is the square root of L from down here. So square root of L goes here. Cool, and then we can add to that our y-intercept. So that's 0.02, and again we put this in brackets because it's the value and the uncertainty in the value. 0.02 plus or minus 0.07. Cool. So that's how we write the equation. And next what we're going to be looking at is how the equation we got from our experiment to what theory would suggest. The way we do this is by taking the theoretical equation from the front sheet here. I've rewritten it again in taking out a factor of square root of L, because that leaves all the stuff here in the brackets, and all the stuff here in the brackets, they're all constants and they represent the gradient. So all we need to do here to work out what the theoretical gradient is just substitute in each of these values straight into a calculator and work out what it should be. So the gradient in theory is equal to 2 pi square root 1 over, and the value for g I'm going to use is 9.81. So I'm going to bung all these things into my trusty calculator. And I get a value of 2.006. So now I can make some sort of comparison between what theory suggests the gradient should be and what my gradient is. What I like to do is what I call TIE fighter diagrams. So here is my gradient 2.0, and my gradient has uncertainties. So my gradient could be anything up to 2.1 and down to 1.9. So that's just the gradient plus the uncertainty, and the gradient minus the uncertainty in the gradient. and then I can plot against that so this is my experiment here, and I can plot next to that what the theory suggests. The theoretical value is here. So you can see that this value is well within my experimental errors. Now what you can do as well, usually there's some sort of value that you have here that also has uncertainty in it. G isn't usually given with uncertainty. The uncertainty is very, very small. But let's imagine that G, instead of just being equal to 9.81, let's imagine that it's got an uncertainty of 0.01. So what can we do with that? Well, what we can do here, we can do the same calculation. How do you even spell theory? The same calculation, but we're going to work out a max value. Okay, so that means I can do the same thing, 2 pi square root 1 over g, but this time I'm going to do 9.81 and I'm going to add to it the uncertainty. This is actually going to work out the minimum value, not the maximum value, but you get the idea. So I can go back to my calculator and I can put these values into the equation this time. So I've done the calculation now and I've got a value. It's very close to the actual theoretical gradient because I haven't added that much uncertainty. But you can see that there is a slight difference here, which means now we can calculate an uncertainty in this theoretical gradient. And the way you do that is by finding the difference between these two here. So delta M theory, so the uncertainty in the theoretical gradient, is 2.006 minus 2.005, which means 0.001. It has the same units as the gradients from above, so seconds per square root of meter. So this is the uncertainty in this value up here. So I could add it up here now as well, plus or minus 0.01. And what that looks like over here, again, it's a really small value, so you can add little error bars here. This is exaggerated, so it looks like this error bars come right out to the point, but it shouldn't be anywhere near it. But you get the idea now that what you're not just comparing these values in the middle, you're comparing the values plus their uncertainties. So what we're going to look at next is statements you could make about different amounts of overlap. The advantage of these TIE fighter diagrams is that it's quite easy to make a statement about the strength of the relationship between the experimental values and the theoretical values. I'll show you what I mean by that. Here I've got some diagrams to show you what I mean. So if the uncertainties line up like this, it doesn't matter which one's the theoretical and which one's the one from your equation. If they line up like this is a strong relationship. If they line up like this, then there's some relationship here. Notice that this error bar here doesn't extend out past the midpoint of this first error bar. Either of these, it's fine to continue with this data. Then we get down to the relationships that might need you to do some retesting of your data. This is a weak relationship. You'll notice that this, the middle point of this error bar here, falls outside of this set of error bars. So you might need to retest some data for this, or relook at your lines of best and worst fit. And then the final relationship is this one here, which is no relationship. So there is no overlap between the uncertainties, the error bars of these two points. So this, you definitely need to collect some more data, sadly. So as well as comparing your theoretical gradient and the experimental gradient, you need to compare your theoretical y-intercept to the theoretical y-intercept. The y-intercept here in theory is 0.0 because the original equation has nothing added to the end of it. So the only thing you can add to this and not change the equation is 0. So the theoretical y-intercept is 0. Here I've got my error bars, sorry, the uncertainty in my experimental y-intercept, and you can see that it's a good correlation. So the final thing you need to do is write some sort of statement about the quality of this relationship. So what this statement might look like is something like this. My experimental results show a strong relationship with the expected theoretical values. You could go into why that is, but it's not necessary. So for the next video, we're going to possibly talk about discussion, or we might just change tack altogether and start looking at some mechanics. Good luck with this. Cheers.